So today, first we are going to again derive that equation, the state line equation, and we are now using the other half cell, and this would be the state line equation of water half cell at anode because the water is at this side, and there is only one option for this water to reduce to oxidize, and when it is oxidized, it must be at the anode. So this is the simple understanding over there. So now what is the equation? Again, you can write the Nernst equation is equal to E naught minus 0.0591 over n. And here are the four log of product divided by the reactant concentration. Product is the water, oxygen, and the hydrogen. Again, these are in the molecular form. They are considered to be unit concentration, and your equation becomes like this. And in similar to the first derivation, now this is you can just open by using the mathematical formula log 1 over a over b will be equal to log a minus log b, and log 1 minus log hydrogen ion concentration, and log 1 would be equal to 0. So that's why it is not written over here. So this will be the minus, and log hydrogen ion power 4 because the coefficient over here is the 4. And when uh, there is any coefficient, it will, the power becomes the coefficient when you take the log or the log natural. So this 4 is cancelled out. What is left? Minus log is hydrogen ion concentration, and this will be equal to the pH. And now you can put the actually in put the value of the pH in here, minus log in place of the minus log hydrogen ion concentration, and equation will become like E is equal to E naught minus 0.0591 pH, and E naught here is the 1.229 or 1.23 minus 0.0591 pH, and this is the final equation. This was the second option at the anode, and I'm not going to derive this one. You can use this half cell, do the similar steps, and finally you will reach at the same equation, that is is equal to 1.23 minus 0.0591 pH. So importance over here is, again, this is the graph we have discussed. So right now I have derived the Nernst equation to have the state line equation for the both half cells. Now, what is the purpose or importance of these two state line equation? One is the with intercept, and this is without intercept. And the importance over here is you just put the value of the pH, and you can easily get the value of the cell potential. So there is no need to use the Nernst equation by using the hydrogen ion concentration or the hydroxyl ion concentration. So that's why we have derived earlier, and now you can just put the value and get the value of the cell potential. So again, you are going to plot the graph with the pH versus the potential. And let's suppose if this is the this first half cell, if you put the value of pH, the first is the 0, then it will become 0. E naught, this will be the only value, 1.23, and 1.23 is here. Now similarly, now you can put the value 1 2 3 4 5 6 7 8 9 10 up to the 14, and it will going to decrease up to the value of the 0.401, or somewhere it is written 0.403. All are the correct values. Similarly, you can do the procedure by using this. It is the without intercept. That's why it is passing through the origin, coming down with the minus 0.829 value. So first I'm going to discuss, as we have earlier discussed, this is the stability line, and the metal ions or the metal which are present within this field are stable, and any of the metals ion above this field or metal below this field are the unstable. Let's suppose one of the example I'm going to show you. If this is the half cell of the water, 1.23 at 0 potential, and if any metal is having the potential less than this, that means 1 point, let's suppose 1, that means this is now the water is having more potential as compared to metal ions. So this is not going to be oxidized because of having the more potential as compared to the metal ions. So I will give you later on the example. By using the example, you will easily understand over here. But here, just only to understand, all this field actually it is called the stability field, and outside is the unstability field. So let's do with some of the example. And this was the first example we discussed before, and we actually left the answer there to discuss the stability of the metal ion or the metals with the water. So here I'm just going to discuss over here the stability of the iron. So if this is the iron, again I am repeating again and again the same answer. If this is the iron you are going to consider, then it must be at the anode, because there is only one option for this iron to oxidize, and when this is going to oxidize it must be at anode. So this potential must be at the anode. And similarly, if this is oxidized and the appropriate water over here is this, because this is the opposite, and then this water will reduce to the hydrogen and the hydroxyl ion concentration. So actually, we were discussing the rusting. If the iron, by looking at this is the less potential and this is the more potential. When you get the cathode, this is the E cathode minus E anode, then your answer will be in minus. So minus mean this iron is not going to react with the water. So this was the question actually I raised during the start of this lecture. So important over here is to note that these are the standard conditions. Standard condition mean when all the metal ions or the hydrogen ions or the hydroxyl ion are the unit concentration. When all the concentration are unit concentration, then you can have these value, and these value are called the standard cell potential. But there is not always necessary that you have the standard cell potentials or you have the unit concentrations, because in a laboratory you may use more than 1 molar concentration, or it is maybe the 0.1 molar concentration. It is not the unit 1 molar concentration, or it is not always we are taking 1 molar concentration of the ferrous ion. You can take any of the concentration. So when you are going to take any of the concentration, that means now we are going to discuss the non-standard condition. So simply non-standard conditions are when there is no unit concentration of all the metal or hydrogen or the hydroxyl ion. So these conditions are the non-standard condition. So for a laboratory purpose, or for a being a chemist or as a researcher, we are going to have the uh, possibility to have the non-standard condition in the laboratory. So because we are not always working with the standard conditions. So these are the standard conditions. So you might be thinking, no, if you have the water, that means this is not going to react with the water. The reason over here is because this is a standard cell potential. That means it is the unit concentration of the hydroxyl ion. So look at your water is not having the unit concentration of hydroxyl ion. It is the neutral water. So when the water is neutral, that means it is having the pH or the pOH is 7. So it is, that's why this is the neutral water. So that means naturally water is neutral, which is not having the 0 pH or the unit concentration of the hydrogen ion. It is having the exponent minus 7 concentration of the hydroxyl ion or the hydrogen ion, or you can say having the pH is 7. So important over here is the pH. Now pH going to control the reaction. So let's see what is happening at the pH 7. As and this is, you can use the previous equation to calculate the potential. Just put the value of pH over there and you will find the potential of this half cell will be 0.816, and the potential of this half cell at pH 7 will be minus 0.414. So now you again think about if you are putting the iron or you are considering the rusting of the iron in water. Actually, water is this at pH 7. Usually, it may be a little bit acidic, it may be a little bit basic. And as a chemist, now you can exactly calculate what would be the potential by putting the appropriate pH over there. So I'm just here I'm going to consider, let's suppose if the water is neutral, the pure water is having the 7 pH, then its potential is minus 0.414. Now consider again the possibility whether this is going to react, this iron is going to react with the water or not at pH 7. Now again, this must be at the anode and this must be at the cathode. Again, now you can calculate this because E cathode minus E anode minus 0.414 minus then formula and then you put the value minus 0.447 and your answer would be positive. That means now this reaction become a spontaneous reaction having the positive pH at pH, positive cell potential at pH 7. So this is the reason. So actually what we were thinking about, we only just consider the standard cell potential, not the real values. But in case of the neutral water, the pH is 7. When the pH is 7, the potential are reduced to the this one value. So what is happening again? Now if the pH is 0, in this case, now let's see at pH 0, when you put the value, you will get the cell potential is 0. Again, I'm not going to discuss over here because I have already derived the equation. You just put the value pH over there and then you can get the cell potential is 0. So again, E cathode minus formula and minus 0.447, you will get the value of plus 447. Again, this is the spontaneous reaction. That means at pH 0 or pH 0 mean that is the unit concentration of the hydrogen ion, then this rusting or the oxidation of iron is much faster as compared to the 7 because there is having the much more positive values as compared to the this value. And when it is having a neutral at the standard cell potential, then it is having the 0.8277 or minus 0.823 at standard. Standard mean here, don't be confused over there. This is the hydroxyl ion concentration. That means unit concentration of the hydroxyl ion, the pH would be 0. When pH would be 0, pH here would be 14. So pH plus pH will be equal to the 14. So this is the actually the explanation over here why the rusting is happening in place of the water. When you put the iron inside the water, the rusting is going to start, or you can say simply the oxidation is going to start. That is due to the cell potential is not standard. It is the cell potential at the non-standard condition having the pH 7. So this is another explanation. I am just leaving this one because of the time. So maybe later on, or maybe you can just take the picture and decide what would be the spontaneity or the reactivity of this iron with this water molecule. I have already put all these value, and you can compare yourself and in a same manner I have explained in this slide. Now this is I'm going to